Hello and welcome, everyone. My name is Hannah Mason. I'm a technical editor at Composites World. I want to thank you for joining us today for this webinar titled UV Curing for Composites Manufacturing, brought to you by Composites World and presented by allnex. In this presentation, allnex will briefly review what UV curing entails and compare the advantages and challenges of energy curing with thermally curing technologies. Our presenter today, as you see, is John Shaw, Technical Service and Business Development Manager at allnex USA. John has been at allnex for the past 25 years, working on UV cure technologies for coating and composites, and has a long career before that at places like Wright-Patterson Air Force Base and Sherwin-Williams. So he's the perfect person for this presentation. Following his presentation today will be a Q&A session. So attendees, you're welcome to submit a question on the Q&A field on your screen at any time during the presentation, and then we'll get to as many as we can at the end. I do also want to note that the webinar is being recorded and will be sent to you via email from Composites World when it's ready to go, so you'll be able to watch it back later. And with that, welcome, John. It's all yours.
Thanks very much. Good morning, good afternoon, good evening, wherever you are. Appreciate you guys joining for today's presentation. As mentioned, we'll be going over what UV technology is, reviewing some of the advantages and challenges of UV and comparing it to other cure technologies. We're looking at properties of the matrix used for UV cured composites, show you some examples of where it's being used today, give you some thoughts on where it might be going in the future. And then allnex has a line of products for UV curable composites, our Raylock C product line, and we'll go over the materials in that line as well at the very end. Just a little bit about who allnex is. We're a $2.3 billion company. We're global. We've got 33 production sites around the world. We are the global market leader in industrial coating resins. So in addition to the production sites, there's 24 labs around the world, 400 technologists supporting R&D and customers in resin innovation. From a market presence, we divide ourselves up into mobility and transportation, packaging and consumer goods, construction and infrastructure. Composites are a separate growth area for us, so it's a group unto itself. As I mentioned, we are global, predominantly in Europe, but also have a significant presence in Asia and also in the Americas. And from a technology perspective or a chemistry perspective, we do make materials across a wide range of technologies, polyesters, acrylics, amino resins, you can read all the different technologies that are there. And this just into a little bit more detail. From a technology standpoint, we divide ourselves up into liquid resins and additives. So these are conventional water and solvent-borne resins for coatings, adhesives, printing applications. We do have the radiation curable resins, and that's what we're going to focus on today. But the company also makes powder coating resins and then amino cross-linker resins for the various key segments also shown on this slide. So let's just give you a little flavor of who we are. We operate, like I mentioned, across a wide variety of technologies and can bring those different technologies to bear on a bunch of different problems. So just a couple quick background slides. I'm sure that most people already know this, but just to get us rolling. In the world of polymers, in order to get good physical properties, good tensile properties, high modulus, chemical solvent resistance, whatever properties you're looking for, in general, you need to get to high molecular weight. However, as shown on the chart there, as you go to a higher and higher molecular weight, viscosity goes up accordingly. And normal application methods require some reasonably low viscosity material for flow, fiber wetting, air release, in general application. So in a lot of applications, we're going to start with a low viscosity liquid and build up to high molecular weight to make the composite, regardless of whether it's UV or thermal. And if we look at the difference, most two-component systems build molecular weight through a stepped growth process. and you only achieve high molecular weight or only achieve those good properties at high conversion. As you can see on the chart on the lower left, the step growth materials start out as monomers and then dimerize and then trimerize and take a long time to build up to that high molecular weight. So it takes a long time in high conversion to get to high molecular weight and good properties. UV curable coating resins build molecular weight through a chain growth process. We get high molecular weight even at low conversions. Part of this is because free radicals are unstable and very reactive, and the other part is that the growing radical chain ends can react with any other acrylate or methacrylate group. There's really no stoichiometry involved. So you get high molecular weight right away, and then continue building a high molecular weight as the reaction increases. But you do get the high molecular weight almost instantaneously, and this is why UV is such a fast cure process. So with that little bit of background, let's dive into what is UV curing. And this is a process where we use UV energy or occasionally visible light to convert a liquid formulation into a solid material. Other processes would be using heat or solvent evaporation or oxidation, but here we're using UV energy. And that energy is in the ultraviolet, 200 to 400 nanometers. So if you see at the bottom there, you have the electromagnetic spectrum. Rad cure or UV curing plays in the ultraviolet, and everybody else plays in the infrared or thermally cured systems. And why is it used? Well, we mentioned earlier that it's a very, very fast process, and that's generally the driver for people looking at UV. It only takes seconds or minutes to cure with UV, and so your productivity, your throughput goes up accordingly. So it doesn't take hours to cure things, seconds, usually seconds, perhaps minutes if it's a particularly slow process, but even so, UV is generally a faster process to cure things than any other technology. It's also a cure-on-demand technology, and I think this offers a lot of advantage as well. There's no reaction in a UV system unless it's exposed to UV energy. In thermally cured systems, once they're mixed, even at room temperature, there's thermal energy available, so they start reacting, and that means that there is a definite pot life, and it's usually reasonably short. With UV, if you don't expose your formulation to UV energy, it's got an extremely long shelf life, extremely long pot life. So it'll last a year or more in a drum fully formulated. This also means it's easier to clean equipment. As long as the UV material hasn't been exposed to UV light, it doesn't start to cross-link. So it's very easy to clean off the equipment, clean pipes, clean everything else. It also means there's a stable viscosity. With two component systems, once you mix them together, reaction does start taking place, and eventually your viscosity will start to build. With a UV system, the viscosity is fairly constant because it doesn't react until it's exposed to UV light. So productivity, cure on demand, probably the two big things. We find from our customers that if you compare things on a cured part basis, UV can often have a lower overall cost. Part of that is it's 100% solids, the cure speed is very high, and you can recycle material if it hasn't been exposed to the UV energy, so you can reuse it. Mentioned before, these can be single component formulas, so you don't have mixing errors. There are fewer regulatory concerns. It's very easy to make these styrene free. And finally, the energy costs for UV lamps are generally lower than for ovens, and with the shorter cure time, you're generally using less energy to cure with UV than you would thermally. There are some challenges that come with UV curing. The biggest one being it's a line of sight curing. All areas of the part or composite have to be exposed to UV energy to cure. You can't just illuminate one area and expect the cure process to spread out to the entire part. So everything has to be exposed to UV. It's not terribly difficult to do. It means that the lamp's placement is critical, but that's generally not difficult to do. You do have to be cognizant of the absorbance of the system. Components that absorb UV energy can compete with photoinitiators and possibly interfere with cure. There's ways around that, and we'll talk about that later. There's also shrinkage. Everything shrinks. Anything that reacts is going to have shrinkage associated with it. That's well known with just about any system, and in UV systems, you can mitigate that through your selection of diluents and oligomers. So some challenges for UV, more things that you need to be aware of, not necessarily things that are going to prevent you from using UV. So again, comparing UV to a peroxide cured chain polymerization process, just want to focus on a couple things. For initiation, you're going to have a peroxide that's your initiator or some initiator that will break apart to form a radical. That radical adds to a monomer or an oligomer, and that starts the process. And then there's propagation and chain growth. And finally, when two radicals come together, the process is terminated and you've got your final material. With UV, it's pretty much the same process. It just starts differently. So with UV, you'll have a photoinitiator instead of a peroxide. That absorbs UV energy and breaks into radicals and forms radicals. And those radicals do the same thing. They'll add to a monomer and then propagate as you add more and more monomers onto the growing polymer chain, and finally terminate when you get two radicals coming together. So if you're familiar with thermally initiated free radical polymerization, it's not that big a step to move to UV initiated free radical polymerization. The other thing to note is that in the termination step, there are two radicals that are necessary for termination, while there's only one radical necessary for propagation. That means as you increase the radical concentration, you increase termination rate. So I bring it up because often the philosophy is more is better. And in the case of UV, people are tempted to throw in more and more photoinitiator to make things happen faster. But what you're doing is you're increasing the termination rate. And so you may cure faster or you may solidify faster, but you're making you're making a different polymer. You're making a shorter polymer. And that could adversely affect your end properties. So the caution here is to use photoinitiator sparingly and not fall prey to the more is better philosophy. So if we just take a quick look at UV versus thermal, UV is usually a chain growth process. Thermal can be either chain or step growth. UV is initiated with UV, obviously, and thermal curing is initiated through heat. UV is very, very fast. Thermal is generally slower. UV curing is single component with long pot life. Thermal curing is generally two component with shorter pot life if you count peroxide as one of the components. But UV is a line of sight cure, and you don't have that issue with thermal curing. So if you think back to the beginning, UV curable formulations are a potential route to starting off with a low viscosity blend, hitting it with UV energy, and creating high molecular weight materials that form your composite matrix. But what goes into a UV curable formulation? So this triangle gives a rough idea of the components and their relative quantities. Oligomers will always form the base of your formulation. They're responsible for bulk properties. So whatever the main property you want in your material or the main couple properties is generally drives your selection of an oligomer. Diluents are primarily used for viscosity control. The oligomers can be pretty viscous, and so to get it down to an application of viscosity, use the diluents. The nice thing is these will react into your system, so there's no volatiles coming off. They can affect properties. They can improve cross-linking and help your properties out that way, but they're mainly used for viscosity control. Not going to go into additives just because there's so many of them here, but they're responsible for fine-tuning the performance of your material. And finally, you'll need one or more photoinitiators to absorb the UV energy and kick off the cure reaction. There's a lot of different oligomer types, but in general, we tend to stick to epoxy methacrylates or epoxy acrylates and urethanes, and sometimes polyester acrylates as well. Epoxy methacrylates are basically equivalent to vinyl esters without the styrene, so it's the same general structure. But these are economical. They're fast curing. They're a good base for a lot of different polymer matrices. The urethanes are tougher materials, can be very good for exterior applications, and the polyesters are in general there to act as a co-resin. They can help with pigment or filler wetting properties, blend in to get lower viscosities, that sort of thing. And again, if we just look at generic structures, the epoxy methacrylates, as I mentioned, are very similar to the vinyl esters. High tensile strength, low elongation, high viscosity will require the diluents to get down to an application viscosity. The urethanes, because of how many different raw materials we can use to make our urethane acrylates, have the broadest range of properties, can be very low functional, can be very high functional, can be hard, can be tough, can be highly flexible. And the aliphatic urethanes are very weatherable materials. So if you want to use a composite in an external or exterior application, then the urethane acrylates come highly recommended. And again, the polyester acrylates generally used as a co-resin to help out with pigment or filler wetting, help out with viscosity. But again, there's a lot of different types that we can make and a lot of different properties we can generate through manipulation of the raw materials of polyester acrylates. So those are the basic oligomers. The diluents were generally characterized by how many different acrylates are on them. So monofunctional monomers, difunctional monomers, tri and higher functional monomers. The lower functionality materials are generally better at reducing viscosity, but are a little bit slower in cure speed. And when I say slower, that's still relative to the other types of UV cure speeds. So everything is going to be very fast. It's just within that very fast realm, the monofunctional materials are slightly slower and the higher functionality materials are slightly faster. And this chart just shows the other effects that monomers and monomer functionality can have on properties. So as you increase functionality, reactivity tends to go up, solvent resistance, tensile strength, and shrinkage tends to go up. Conversely, flexibility, elongation tends to decrease as you go higher and higher in functionality. So while monomers are used primarily for their diluent effect, just be cognizant of the fact that they also have an effect on other properties. I just put in there just to compare to styrene. Styrene's it's a great monomer. It's high TG. It's got great solvency. It's got some regulatory issues, but from a viscosity standpoint, it's excellent. Nice low viscosity, but it's got a relatively high vapor pressure, so it's going to be volatile. If we look at a couple typical monofunctional and difunctional acrylates, isobornyl acrylate and hexanediol acrylate, they also have very, very low viscosities and very, very good diluency, but the vapor pressure is a lot lower. So the odor, the volatility is much, much lower compared to styrene. So if you're thinking about going styrene free, these are two materials that you might want to take a look at as starters. Additives, as I mentioned, we're not going to talk about too much, except to say when you're looking at additives, for a UV system, make sure you understand if they absorb in the UV or not, if they're going to interfere with the photoinitiator trying to grab that UV energy from the lamp, whether they're reactive with acrylates, whether they're compatible with acrylates. And finally, there's a lot of areas in composites where you don't want fugitive materials. And so there are UV curable additives that will react into your polymer matrix for greater permanence and won't be extractable. So just some things to think about when you're looking for additives. And finally, we get to the role of photoinitiator, and we're going to spend a little bit of time here because it is critical to the performance of a UV system. Again, the role of the photoinitiator is to absorb the UV light or UV energy to form an active species that then reacts with the monomers or oligomers to initiate polymerization. Photoinitiators absorb at specific wavelengths, and you want to try to match the absorbance of the photoinitiator with the emission of the UV lamp. That will provide the most efficient cure. So UV lamps, while they do give out energy across the UV spectrum, that energy is concentrated in some areas more than others, and you want to choose photoinitiators that make the best use of the available energy. The last part is photoinitiators are pretty thermally stable. So they only react with UV energy, not heat. And this is part of the reason that UV systems have such a long pot life or shelf life. And this chart just shows several common photoinitiators on the left side there, where their peak absorbances are. Most of them have an absorbance around 240, 250, and another one around 330. And then you notice a couple down near the bottom that also have very long wavelength UV absorbances, the TPO and the BAPO. And these are materials that absorb in the areas that some of the newer lamps, the UV LED lamps, put out their energy. So they're very useful for curing with UV LED lamps. And then a couple general comments about UV formulations. Pretty much every UV material or UV curable material, every acrylate or methacrylate will have some type of radical scavenger in it at the 100 of ppm level. There's generally quinone types, and these help prevent premature gelation or reaction. Key thing to note is that the quinone type requires oxygen to work. So a lot of people have a desire to nitrogen blanket materials or to put an inert atmosphere over partially used drums or full drums. Don't do that here. That will render the radical scavengers or the stabilizers inert and greatly increase the chance of premature gelling your batch. So dry air is great, lean air is great, but there's got to be some oxygen in there for the radical scavengers to work. They generally have no effect on cure speed. They may have an effect on labeling. Regulations are changing fairly rapidly everywhere. So check the SDS. If there's an issue, there's oftentimes, if you come talk with us, we can put different stabilizers in the system if there's something that's causing a labeling issue. So just understand that regulations are changing, and the stabilizers may have to change along with them. And finally, if you have drums or totes or whatever, try not to reheat them multiple times. Every time you heat up a tote, you are consuming a little bit of that stabilizer. And if you do multiple reheats, you may reach a point where you've consumed all of the stabilizer. This isn't a couple reheats. This is, multiple 6, 7, 8 reheats. But just try to avoid multiple reheating of UV curable formulations because you are consuming the stabilizers when you do that. UV systems are generally non-flammable. And then just as always, read the SDS, wear proper protective gear, and follow industrial hygiene. In general, that means proper gloves, glasses, safety glasses, and some kind of covering lab coat. And then wash your hands when you're done. And there should be no issues. So we've talked about formulations and photoinitiators. Now the other part of UV curing is the UV lamps. And there's generally two types. Conventional lamps, these are mercury-based. They can be arc lamp or microwave initiated. As I mentioned, these are full spectrum lamps. They put out energy across the entire UV region. You can adjust how that UV power is distributed over the UV region by using different bulbs that have been doped with other metals. And we'll show that in a minute. More recently, there have been UV LED lamps that people have created. And I got to give credit to the lamp manufacturers. They've increased the power and improved the power and efficiency of lamps quite a bit over the last few years. The big difference is that these lamps are electronic and have a very narrow emission range, whereas the mercury-based lamps put out energy across the spectrum. UV LED puts out energy in a very narrow band, a very specific band in the UV. So you've got to be very judicious in which photoinitiator you select to use with UV LED lamps. And just to give you an idea of what these look like, you have a bulb with mercury and an inert gas, and you either form a plasma using an arc or microwave radiation. You can focus that energy using reflectors, or you can create more of a flood effect. And also understand that in mercury bulbs, the energy from that lamp is roughly 1/3 UV, 1/3 visible, and 1/3 heat. So there is some heat coming out of the front of a conventional lamp. So if we look at the comparison, UV LED, the bulb lifetime is many, many, many times as long as a conventional UV lamp. They are mercury and ozone free, but they have very narrow output. So your PI selection is critical. UV LED, because they're electronic, instantly start when you flip the switch. Conventional UV takes a few seconds to get the full power. As I mentioned, conventional UV puts out heat out the front of the lamp, and UV LED does not. And UV LEDs are generally small, modular, and can be handheld, so they're easy to manipulate on a line or in a handheld configuration. And finally, we talked about the binders, the oligomers and monomers. We talked about UV source, the lamps, and then the photoinitiator. And when you're developing formulations or using formulations, you have to be cognizant of all three. You have to know where your lamps are putting out their energy. You have to know where your photoinitiator is absorbing. You have to know what elements in your binder may compete with that photoinitiator for the UV energy. So all of these things work in tandem. You really don't develop one without thinking about the other two. So UV chemistry, cure on demand, process very suitable for glass fiber composites, wide range of raw materials, very fast process. But again, and I'm going to emphasize this over and over, you have to consider the interaction between the lamp output, the absorbance of the photoinitiator, and the formulation in order to get a good curing situation. So what are some things to consider when you want to use UV in a composite formulation? And here are three general considerations: cure depth, composite temperature, and fiber sizing. So fiber selection is going to have an effect on the composite. And this pretty much means you have to use glass fibers. Composites, if you try to do UV curing with a carbon fiber composite, the fibers just pretty much absorb all the UV energy, and you can't really get any kind of through cure in a composite. So if you want to go with UV, you pretty much are going to be using a glass fiber because the glass is reasonably transparent to the UV. Even so, as you can see in the bottom picture there, the thicker you go into the composite, the lower the energy level is, and the slower the cure is going to be. So there's a practical limit to how thick you can make a glass fiber composite. And if we look at that, we did some experiments where we varied composite thickness and tried to cure it, and then looked at the double bond conversion on the bottom of the composite, or the side opposite the lamp. And as you can see here, we had two different formulations, but they both kind of behave the same. Up to about 8-9 millimeter thickness, you get very good cure. Once you get beyond that, you still get a cured material. It's a solid material, but if you measured either conversion or TG or some physical property, you're going to see that property start to decrease when you get up around 9-10 millimeter thickness. There are solutions. One way to deal with that is if you put a little bit of peroxide into your system, the heat of reaction of the UV cure is sufficient to kick the peroxide cure off, and that way your composite will continue to cure even at thick, at very thick depths. So you can see here, the blue diamond or the red circles indicate the properties falling off around 10 millimeters for just a straight UV cure. But if we add a little bit of peroxide, then we're back up in that 90+% conversion, and the physical properties are similar to thinner materials. So it's possible to cure very, very thick materials by adding some peroxide or some other thermally cured component. It does mean that you're bringing pot life back into play. But if you need to cure thick components, you can do it this way and just use the heat of reaction of the UV to drive your peroxide. From a temperature standpoint, in UV curing, you can get heat from two sources. The lamp, as we've shown before, the mercury lamps generate some heat, and the chemical reaction itself of the UV cure generates a lot of heat. So in thin films, in a typical UV coating, the surface area to bulk ratio is very high and the heat can be easily dissipated. For composites, they tend to hold the heat in because they're a lot thicker and the heat's not easily done away with. And so the temperature of the composite can get fairly high. That may or may not be an issue, but it's something to consider. Higher temperatures generally increases the extent of reaction and increases the cure speed of the reaction. So that could be a positive. Depending on your line configuration, higher temperatures means longer cool down times before you're going to wind, say, pultruded rods up in a coil. Could have an adverse effect if you're doing a pressure vessel or some other winding application where you have a heat-sensitive liner, or sometimes you are winding composites around a material that has sensitive, temperature-sensitive interior parts, in which case you have to control that peak temperature of the composite during cure. And again, these are things that you need to consider, not necessarily things that stop you from doing what you want to do. So just to show you in this diagram here on the left, the blue line is a formulation where I've left out the photoinitiator. And when we turn the lamp on, about 35, 40 seconds into the thing, you see a temperature rise, and that is solely from the heat from the lamp. So over the course of 2 or so minutes, we're doing 20 degrees jump in temperature. The orange line represents a fully formulated material with photoinitiator. When you turn the lamp on, you get a very, very steep rise in temperature, and that's due to the heat from the reaction. And then you go back to a slow, steady rise that's predominantly heat from the lamp. So the heat of reaction does generate a big temperature rise in your composite material. And how do you mitigate that? How do you control that? And one way to do that is by varying the lamp distance and lamp power. And what we see here in the chart is, as you start moving the lamp farther and farther away from the part, the peak temperatures drop considerably. And a lot of these UV lamps will have power controls. And if you turn the power down on the lamp, going from the yellow to blue to the orange lines, you also see a drop in peak temperature. So there's a lot of ways. If you're dealing with a temperature sensitive situation, there are a couple different ways that you can modify the cure process to reduce the peak temperature that your part is going to see. Now, the slight downside is that the reaction rate, I mean, part of the reason that the temperature doesn't get so high is the reaction is just a little bit slower. It still reaches complete cure, but it does so over a slightly longer period of time. And so the reaction rate is a little slower, but your peak temperature is lower, and you just need to run a little bit longer. And we're talking maybe an extra minute or two. So still a very fast process, just not as rapid as it could be if, as I've said, you need to control the temperature of your system. And finally, and this I think we all know, fiber sizing has a big effect on physical properties of composites, and UV curing's no different. So what the chart here shows is the short beam shear strength versus different sizings on the glass fibers. And you can see a considerable difference in the strength of these materials based on the sizing alone. So everything was held the same. The glass fibers were the same except for sizing. The formulation was the same. The cure process was the same. And the sizing is the only variable here. And you can see it has quite a big effect on final properties. The nice thing is that most major glass fiber suppliers have grades of their glass fibers with specific sizing for UV curing. So if this is something you want to consider, make sure you talk with whoever you get your glass from, and make sure you're getting the glass fibers with the sizing that's specific for UV curing. A lot on this slide, I'll just touch on a few things. UV cured systems are limited to glass fiber, thermally cured systems, all fiber types. We've talked about cure process. UV is a couple minutes. Thermally cured systems are longer at higher temperatures. UV is cure on demand. Thermally cured systems are have pot lives and have shorter lifetimes. From a styrene standpoint, UV cured systems can be made easily styrene free. Thermally cured systems, that may or may not be the case. Cleaning is a lot easier with UV because unless it's exposed to the UV energy, it's going to still be a liquid and very easy to clean up. And resin waste, there's a lot less waste in UV system because that until it gets exposed to UV, the material can be used as long as you want. So some advantages there for UV curing. So what are typical applications for UV? And again, considering that you have to get the UV energy to the part, pretty much all of these are going to be open mold situations. Filament winding is a very popular application for UV. This is a typical thermally cured system where you'll have the glass fiber coming out, going through the resin bath and getting saturated with the resin, laid up on a mandrel. When the layup process is done, that mandrel is removed to an oven where it's going to stay for hours, where it's got to be continually rotated, and that mandrel is now out of service for the entire cure process in that oven. If you switch to UV, the front end of the process stays the same. The fibers go through the resin bath, get saturated, laid up on the mandrel. But now when you've laid up your material, you flip on the lamp, cure in a couple of minutes. You can pop it off the mandrel. You have a ready-to-use part. The mandrel can be reused. This means that often you can have a large capital savings in the number of mandrels that you have to keep around. The resin itself is, again, cure on demand, so very, very long pot life. And energy costs are going to be a lot lower because you're not using that oven for a long period of time. And just some examples. Here's a printing roller where the inside core is made from composite, and pressure vessels, which have been the liner has been overwound with a glass fiber composite UV cure to improve the strength of the pressure vessel. Similarly for pultrusion, diagram's not quite as pretty, but still you get the glass fibers, collect them, they go through a resin bath. With a thermal system, this thing goes through a thermal dye. And so the line speed is going to be dependent on how big that oven is or how big that thermal system is, the heat transfer rate, the reaction kinetics of your system. If you want to change to UV, you remove the thermal oven and put in UV lamps. So converting a line to UV is not a terribly difficult thing. Your line speed is going to go faster due to the rapid UV cure process. The pot life is going to be a lot longer. Physical properties are going to be comparable. And I didn't mention this before, but if you see a lot of variation over the course of a year on your plant floor, say you're operating in the northern part of the Americas or somewhere in the northern regions, where maybe out on the plant floor you see a big variation in temperature between winter and summer, that can have an effect on the quality and the pot life of your thermal systems. But because UV pretty much just depends on the UV energy, UV intensity and UV energy, and not on ambient temperature, you don't see a lot of property variation if ambient temperature varies over the course of the year. And so some applications, you can just make straight pultruded rods, composite mesh. Most fiber optic cables have a strength member in the middle of them, and often this is a UV cured composite rod. And then in the wind blades down there at the bottom of the screen, the spar cap is often the strength in a spar cap is often improved through the use of UV pultruded rods. And because you need so many of them, the productivity of UV comes into play, and you can create a lot of rods in a short period of time to service the wind blade industry. And I mentioned that most of the time things are open mold, but here's an example of some people doing some work where they have the UV is in mold, and you're curing in the mold while the part is being pultruded, and the effect that has is pretty evident here. On the left side, you have in-dye curing. Those parts are nice, smooth, well collimated, and if you look on the right side, you see that these parts aren't as high quality if you're doing out of dye curing. So while the majority of UV curing is done outside the mold, there's a lot of work being done to see what can be done to cure inside the mold and improve composite properties that way. Another area that UV has found a home is cured in place pipe. And if you're unfamiliar with the process, instead of digging up pipes to replace them, you can clean the pipes, insert a liner, and then cure that liner either through thermal energy with hot water or steam, or you can cure it with a UV light that passes down through the pipe and cures that liner in place. So it's a very fast process. It means you don't have to dig up lines, and the productivity and fast cure of UV means that you're done with the process in a very short period of time, rather than the thermal process, which could take hours to cure once that liner is in place. So where might UV go next? And one of the areas is in-field repair. So I mentioned earlier that the UV LED lamps are small and modular and can be made into handheld units. And this allows you to take UV into the field. You can make a composite patch, lay it up on, say, a wind blade or a pipe or whatever you're trying to fix, and cure it with the handheld lamps, usually UV LED. And you get a nice smooth repair, and you don't have to take things out of service. You can cure right there in field. So this is an area I think people are working this already, but I think people are looking to make this a much bigger area. And so finally, where can allnex help you out? So we've been supplying formulations and resins to the composites industry since before 2000, so a considerable period of time. And we have recently, last few years, really decided to focus in this area. So we've created the Raylock C line of materials. And what these are fully formulated, ready-to-use materials that somebody who wants to get into UV curing can use to demonstrate feasibility, figure out if these generic formulations work or not, or what needs to, or how we can tweak them for you. But they are all UV curable, either through mercury or UV LED. The UV process means that you're going to get a high productivity out of your line. These are often sustainable, lower energy, less waste, all contribute to a sustainable process, and they are styrene free. So while we do make a lot of customer-specific materials, these are the generic Raylocks that can be sampled or purchased. And the Raylock C1100 is a very basic material. The Raylock 1101 is a high TG material. You can see the 1100 is about a glass transition temperature of around 100. The 1101 is about 50 degrees higher at 152 degrees C. Raylock 1102 is more of a tough material, and you see that through the high impact strength of 168 versus the other two, which are much lower. And the little radar plot there shows how the three materials compare to each other. So you have the purple is the 1100, and it's just got very basic formulation, does everything pretty well without any one aspect being outstanding. The 1101, the high TG material, has high hardness, high TG, and the 1102 is a material with really excellent mechanical strength, impact strength, and some flexibility. So depending on what your application is, these are materials you can start with. If they're sufficient, that's wonderful. If not, we have the formulation expertise to create something that is exactly what you need. And we mentioned just a couple things. One thing I haven't mentioned about UV system is, yes, they can be very high viscosity, but that is due less to molecular weight and more to hydrogen bonding. And the nice thing about hydrogen bonding is a little bit of heat can break up hydrogen bonding and drop viscosity pretty readily. So the top graph there shows the viscosity versus temperature for the three Raylocks. And you can see, even though they may start a little bit higher than what we normally want for a composite formulation to get good fiber wet out and good infusion, if you just ramp the temperature up a little bit to, say, 35 or 40 degrees C, the viscosity drops precipitously, and you get nice low viscosity for good fiber wet out and good infusion. And the other aspect we mentioned was that photoinitiators don't react with heat. They only react with UV. So the bottom chart shows viscosity versus time. So we held everything at 40 degrees C and followed the viscosity. And you see there's virtually no difference in viscosity. There's no viscosity creep, no viscosity gain over a 24-hour period. And that's, again, due to the fact that photoinitiators react to UV energy and not thermally. So to kind of summarize everything, advantage of UV, it's fast. Cure on demand, it only reacts when exposed to UV energy. It can be styrene free. There's a wide range of raw materials so that you can generate a wide variety of properties. UV LED lamps, I think, are really going to advance curing of the UV curable composites, especially in field. And the big things to remember that there's an interaction of the lamp output, the photoinitiator absorbance, and your formulation. And those things have to all be considered to get really efficient UV curing. And then also that UV is a line of sight curing, and you have to consider the geometry of your part and the absorbance of any other materials in your formulation to make sure you're getting good full cure of your UV system. And with that, I thank you for your attention, and if there are questions anybody has, I'd be happy to answer those now.
All right. Thank you so much, John. That was great. I know I learned a lot. I'm sure our audience did as well. So we have a few minutes now for Q&A with our attendees. So now's the time, attendees. If you haven't submitted a question yet, please do so now. We've got a few in already, so we'll start there whenever you're ready, John.
Yep, just had to wet my whistle.
Perfect. All right, the first question is two parts here. What needed properties would dictate the step versus chain growth reactions? And can you have a short chain build in a fast cure system?
All right, so the first part, whether you want to go with chain or step growth, is basically that's really a function of how fast you want the system to cure. Chain growth is going to be a lot faster curing. And step growth is going to take longer. Now, the one thing that you maybe need to consider, sometimes that fast curing can induce some stress into your system if you're not careful. Again, something to consider, not necessarily something that's insurmountable, but by curing very quickly, sometimes you generate some internal stress, and with a longer thermal or a longer step growth process, you may not see the same degree of stress. So choosing between the two, I would say, is based on how fast you want to cure your composite, and then just when you figure that out, consider whether you're generating some internal stress as you're doing so. And what was the second part? Oh, can you make short chains fast?
Yeah, can you have a short chain build in a fast cure system?
Yeah, absolutely. If you remember those the diagrams that I put up at the beginning showing the initiation, propagation, termination step, if you put a lot of photoinitiator in a system, you're going to generate a lot of radicals very quickly, and you'll get a lot of reaction and a lot of termination. And so the acrylate groups will cure, but because you get a high termination rate, you won't get any long chains produced. So by increasing photoinitiator concentration or increasing lamp intensity, basically the more radicals you create at one time, the shorter your chains are going to be. So yeah, by bumping up photoinitiator and cranking up the lamp power, you can make short chains fast.
Okay, excellent. Appreciate it. Next question. What is the bulb life of microwave energized bulbs? For example, 6,000 to 8,000 hours?
Generally shorter, 2,000 to 3,000 hours.
Okay.
Yeah. And yeah.
Okay. Next question. In considering the tooling needs for a UV cure system, are traditional steel, aluminum, or composite tooling all usable?
Yes. Definitely the steel, aluminum, chrome steel, all very good. The composite tooling there, I think you just want to make sure that the temperatures that your composite is going to reach don't soften the composite tooling that you're using. but they should, with proper mold release agents, everything should release just fine. And yeah, I don't think there should be an issue there. Again, make sure that if it's a complicated geometry, you've got a way to get the UV energy to every area of the part, but there shouldn't be an issue with steel or aluminum tooling.
Okay. So you mentioned, of course, that glass fiber is the preferred type of fiber for this. So we have a couple questions on carbon fiber, which you also mentioned. Yep. Let me find out. Is the use of these resins to rapidly cure carbon fiber composites completely out of the question, even with thin laminates or with the help of peroxide additives? And would there be any trick to reducing UV absorbance?
Part of that you got to ask the carbon fiber guys, but in generally, let me take the second half of the question first because I forgot to mention it. So thank you for asking that question. While all of these resins that I've mentioned can be UV cured, all of them can be peroxide cured as well. So if you want to use them for peroxide curing of a carbon fiber composite, they'll absolutely be fine. They'll work very well. I don't know that you're going to get more than a couple layers of cure if you're doing a composite, a carbon fiber composite, trying to cure it with UV. Even going to long wave UV, which generally penetrates deeper, the fibers, they absorb everything. Some people have tried to mix glass and carbon fiber together, thinking the glass will provide a pathway for the UV to penetrate deeper in the composite. And I think there's been some limited success with that. But you're really not going to be able to UV cure a reasonably thick carbon fiber composite. And then I said that, and then I'm going to come up with the exception. We didn't talk about it, but there's a part of UV chemistry or UV curing that's not very much used, but you can cure epoxy functional resins with using UV cure. And what happens is you have to use an initiator that under UV energy generates an acid. And then once that happens, you're basically in an acid cure epoxy situation. And so you can cure carbon fiber composites using UV, using epoxy functional resins and these special, very expensive acid generating UV photoinitiators. It takes a long period of time. They're not on the same order of magnitude of speed as a free radical type of situation. But if you absolutely wanted to use UV to cure, then that's an opportunity, is to use epoxy resins and this UV initiator that generates an acid, and then you'll cure over, I don't know, 30, 40 minutes with just an acid, just a straight epoxy cure, acid cure.
Okay. Excellent. So we're right almost at the top of the hour here. We'll grab one more quick one here. What's the maximum thickness of the composites you can cure using this?
Most of my answers start with "it depends," but if I would think if it's pure glass and you want to cure it all at once, then and you don't want any performance or any property gradient, then 10 millimeters. If you have something that you can cure from both sides, then you can cure maybe 20 millimeters thick. If you can, now that the other thing you can try doing in, say, for like a filament winding situation, you can wind and cure as you go, or wind and say get 5 millimeters thick and cure that, and then wind again on top of that. And so if you want to cure all at once, it's around 10 millimeters. If you can cure from both sides, you can double it. And if you want to cure as you go, then it's kind of unlimited, if that all makes sense.
Yeah, no, that's great. Appreciate it. Unfortunately, we've come to the top of the hour here, so we do have a number of questions that we weren't able to answer live. These will all be forwarded to John and the allnex team, so they'll be able to kind of respond offline. Obviously, you have John's email as well. You can reach out. But yeah, John, thank you so much again for this presentation. We really appreciate it.
I appreciate you guys setting it up, and I appreciate the audience for sticking around and listening.
Yeah, thank you from Composites World, also to our attendees for joining us. We appreciate you being here. Hope you'll join us for the next Composites World webinar. For more info, visit compositesworld.com, and have a good day, everybody.